Hello everyone, my name's Hayden Nelson, and I'm the Director of Marketing and AE for 4DSP products at Abaco Systems. If you look at that title, it's a pretty long title. I have a lot of things that are involved in that title. I like to make fun of my title because marketing and apps engineering and 4DSP products. If you remember last year, 4DSP was up here as one of these blocks. I think we were right here, a big blue 4DSP logo. A gentleman named Rick Airy came and presented, and I think Abaco was down here. We're just a reminder to y'all in the room. 4DSP was acquired by Abaco Systems. I come on board to Abaco as part of that acquisition. I joined. That had happened about last November, so it's a relatively recent thing, and it's a pretty interesting thing for me to come into Abaco. Great company, really good matching of technology of their kind of core business of single board computers and a number of other electronics, but their FPGA technology has really been augmented by 4DSP's FPGA and our embracing of the Vita standards, things like FMC. So it's particularly relevant to this topic because my background, I used to do a lot of electronic warfare work in kind of the defense, research type labs. I left there and I worked in the commercial wireless space for a test equipment company for a number of years. So I have a kind of a unique perspective on the electronic warfare side as well as some of the commercial wireless aspects that are going on in the industry. So there's some interesting trends that I kind of, in comparisons, I can see between those different industries. So, but being part of Abaco and I'm responsible for the 4DSP products, is interesting because we can really address these electronic warfare system requirements, and we do a lot of engagement with defining of the next generation EW systems, and so that's what I was going to be talking about today. So, for those of you who aren't EW experts in the room, I wouldn't consider myself an EW expert. There's kind of really three areas. We heard the term ECM, electronic countermeasures, was a word that was used. Today we really talk about kind of three different areas: electronic attack, electronic protect, and electronic warfare support. And so when we talk about electronic warfare, we're not really talking about things like electronics like hacking emails or things like that, or that are in the news recently, but we're really talking about the electromagnetic spectrum and dominating that. The wireless spectrum is a resource that we have. It's the people like Sprint pay a lot of money to get access to electromagnetic spectrum to be able to enable your cell phones. On the battlefield, the electromagnetic spectrum is a very, very valuable resource for us as an allied warfighter to go in and be able to detect or shut down our enemy's electronic detection systems, to be able to communicate with our soldiers on the battlefield, being able to pass real-time intelligence. So it's a very valuable resource for the battlefield. And so managing that and being able to deny our enemies access to being able to detect us, say we're coming into a certain airborne engagement. This is kind of the scenario, my cartoon explanation of how I kind of a very simplified view of an electronic warfare scenario. This one's a little violent, actually. That you're coming in with a fighter jet and you got some bad guys down there, the little skulls. And there's some radar, and we kind of traditionally radars are sending out signals to detect an aircraft, and you can electronically capture that signal, do some processing on it, and retransmit it to kind of like maybe spoof out the radar, for example. And so our little orange missile launcher over here doesn't know who to shoot at, so to speak. So this is kind of a classic example. It becomes, there's a number of reasons why we may need to get in and out of an enemy territory. For Abaco, the whole Osama bin Laden thing, we had to go into well, they're an ally, but we had to get in and out of there, and so being able to do that safely is really important to our warfighter. Keeping them safe, bringing them home safe. It's particularly relevant to me because I know a lot of these guys. I'm an ex-military guy. I was in the Navy for a number of years, so I take this. I think it's really neat technology, the way that we do this, but it's also really important for our service members and our allied warfighters. So we heard digital RF memory is a type of system that, or DRFM as the acronym, is a type of system that is commonly used as an electronic warfare compute system. I mean, the idea here is that you have a receive channel where the signal coming from the radar is being received. We kind of down convert it, digitize it, put it through an FPGA, and back out a DAC, and then retransmit it. And the components here, you tend to have different pieces. They're RF, digitization, digital signal processing. FPGAs are really good at this because of their latency. They have a lot of parallelism. You can build a custom DSP architecture. FPGAs are very popular for this type of EW system. And a number of other support assets, some of them more critical, like single board computers, and we're even seeing interest in using GPUs for electronic warfare systems because you have a lot of compute power if you're able to transfer to the memory quickly. And so Abaco has a number of products that address this space, from FPGAs. FMC is a particularly popular one for electronic warfare because of its modularity, and it's relevant because it's a VITA standard, VITA 57.1 and 57.4. So talking about just the ADCs, and it's kind of relevant. It's a very nice lead-in from the previous presentation that we talked about. Latency. I think the gentleman over here, you brought up latency, and that's end-to-end latency is really critical for electronic warfare, because you can imagine that missile coming in, and I'm flying my little fighter jet, and it's detecting me. It's being able to receive that signal and retransmit it to tell that missile that's going to blow me up to go somewhere else and I need to be able to get that back out the door is very critical for this application. And so this whole topic of the interfaces, the digital interface, this JESD204B interface and LVDS interfaces are become really important for this type of application. So I'm going to talk a little bit about the VITA standards. So this is a pinout. I want you all to memorize every pin on here. Right, I'm just kidding. So this is actually from VITA 57.1. So if you're familiar, FMC, it's a great standard for these little low form factor mezzanine cards that plug FPGA mezzanine card. We can overlay this with the types of interfaces, and you can see here that FMC Plus is the coming soon to be ratified standard or defined on VITA 57.4. And there's a number of additions they made from FMC to FMC Plus, all of them around this JESD204B interface that we were talking about earlier. And so the unfortunate side effect of JESD204B is all the serialization, deserialization. You take a latency hit, and that doesn't jive well with the electronic warfare system designer, right? And whereas LVDS has the issue that we have those lots of buses and lots of wires, and that's also undesirable because the number of pins. So if we're looking at FMC, it's kind of interesting that we've seen the PCI to PCI Express. There's an embracing in the analog conversion devices out there. This high-speed serial JESD204B protocol. It's better to have fewer wires but the FMC standard is as it's evolved, it's sort of making a bet on that this is the direction of future conversion devices. And it's probably a pretty good bet. But it also, when we went from FMC to FMC Plus, we had 80 LVDS pairs. We didn't add any more when we got to FMC Plus, so that doesn't help the electronic warfare system. And so this is the idea here is this is a platform challenge. Is as we're going forward, in the interim until these high-speed serial interfaces are able to reduce this latency issue. I think I've heard some optimism around a JESD204C standard to try to do latency, address this latency concern associated with high-speed serial for DERFMs and electronic warfare. But as of today, the preferred method is these parallel LVDS buses. And so there is an additional provision on here, something called extended FMC Plus. And right now that's adding additional 8 high-speed serial lanes. And so with up to 32 high-speed serial lanes on FMC Plus, it's awesome. There's a ton of bandwidth you can get in and out of these devices. But again, the latency concern always comes up around EW. So maybe there's something to be said about this JESD204C if that addresses it. Maybe there's some provisions that the FMC Plus can say, oh well, in the interim we can add LVDS lanes here. And it's interesting to see how many people have approached this problem. Some vendors of FMC, we like to stick to the standard. Some vendors have actually gone out and augmented it and violated the standard, and I'm not a big fan of that because a standard is a standard because of interoperability, that I can use this it's kind of like modular Legos. I want to be able to buy this module from you guy and optimize my system. And FMC makes a lot of sense because I can upgrade it next year. I can optimize my I/O based on my requirements. And so, but again, I think I've made my case case here. So the next piece of the system, another platform challenge is the FPGA. So in an electronic warfare system, we talked about ultrascale is a huge explosion of FPGA resources. Well, back on these A to Ds, another trend I don't talk about here is multi-channel. There's a number of good reasons to add lots of channels, from beam steering to polarization techniques on these EW systems. And so you have not only wider bandwidth, more data coming faster, but you have a lot more. It's like I've added faster data coming in, but a whole lot of streams. So I need a lot more resources. Unfortunately, Xilinx helps us out a lot with this. With massive I/O bandwidth, these ultra-scale devices have a lot of compute resources. The other issue with the FPGA piece is the security, and you can imagine the IP the technique that is built into that FPGA IP, how if that got in the hands of a bad guy, there's actually people out there, there's companies that will take the bit stream from an FPGA and reverse engineer the digital architecture logic to figure out how you're jamming that radar. And it's kind of freaky, that they can do that. There's people out there just to do that. So encryption and securing that IP for FPGAs is really critical for these systems. And so Xilinx helps us out a lot here. They have a lot of nice features in terms of bit streams encryptions. They have some anti-tamper IP blocks that you can put into these FPGAs. So like if someone starts messing with the JTAG chain or messing with the power supply, it'll zeroize the device and just kind of brick it, if you will. So we've seen a lot of the Zynq UltraScale Plus devices that are coming out soon. We've seen a lot of security features, and I think that really helps the electronic warfare system designer. And so kind of the last piece is I have them as two blocks, but they can really be one, as we kind of saw earlier. And the notion here is going forward, there's this idea of, so in the days past, a radar at DERFA may have deployed with a library of techniques. Okay, well, technique A, B, C, that's going to work against threat XYZ. And the operator in the fighter jet's like, I know my intelligence, I'm going to select the appropriate countermeasure for the situation I'm getting myself into. And that's nice, but there's this kind of research area called cognitive EW, and kind of the cognitive aspect, the thinking aspect, is that these systems are able to do kind of an electronic intelligence aspect of this, where they can listen to the signals and determine the environment and adjust the techniques in real time in order to ensure that the asset that I'm trying to protect is actually being effective against that threat. And so the trouble with a cognitive EW is typically those algorithms are kind of neural net learning algorithms, not the best type of algorithm that is a good target for an FPGA. Right? So these tend to have a lot of complex branching and programmed in more higher level advanced languages, whereas FPGAs tend to be really good at a high-speed data streaming type of application. And so keeping the SBCs and GPUs have shown some interest with some of the direct DMA technologies that have shown up around GPUs to be able to stream whenever latency is not as much of an issue. And so kind of the message here is that you sort of need to use the right tool for the job. There's certain threats that you may need some really complex general purpose processor learning algorithm, whereas a simple FPGA DERFA may be appropriate. And so having this is sort of solved by the VITA standards, and being able to interconnect these, maybe even some of these optical interconnects that you can put these kind of in a back of an aircraft and have an optical interconnect to the back of it, for example. So there's the challenges are many. The latency one is the one I tend to get a lot of questions about, and it comes up quite a bit whenever I talk about GSD and LVDS. And we tend to talk about all these the swap constraints tend to come up quite a bit, because these need to be highly secure, highly rugged, highly tested type electronic warfare systems. That they are mission critical. So oftentimes the difference between life and death. This is an example of an EW, an airborne EW system that we've worked with as part of 4DSP. And actually, I think we spoke about this last year. We call it our VPX 167. It's a airborne pod, with all these different technologies integrated in. It's a 7 built on standards. It actually has something called Flex VPX backplanes, where we can kind of have a virtual 7-slot VPX chassis, but the backplanes are sort of back to back, so you can insert the cards in from end to end, so it fits that nice form factor that'll fit into an aircraft pod. And so, and I guess the message for you all is with the joining of forces of 4DSP and a number of other technologies that we're able to bring to bear within Abaco, we're going to be making a larger focus in electronic warfare in the coming years, and to me it's a pretty neat application area. I have kind of an interest in it just because of it involves RF, DSP, and that's another big challenge of this, is that you tend to need different types of engineers to design the different pieces. And so working with a trusted partner who can help guide you, I think, is also really important to being successful in this space. So with that, that's all I had. I appreciate your attention.